Hello, chemistry students. Today we are going to talk about nuclear chemistry. And first up, we are going to do the definitions of nuclear chemistry. Nuclear chemistry is the study of the nucleus, the atomic nucleus, its reactions, and radioactivity. Radioactivity is the spontaneous emission of particles or energy during nuclear decay. The nucleus breaks up into smaller pieces. Energy is just electromagnetic radiation, and particles are pieces that have mass. So like we just talked about, nuclear decay is the spontaneous disintegration of a nucleus, or when a nucleus just automatically breaks up into smaller pieces. Most of the time it results in a totally new element, and it occurs when particles, and we'll talk about what type of particles there are in nuclear decay, and or energy escape from an unstable nucleus, and it releases large amounts of energy, much greater on a mass per mass basis, much greater than chemical reactions. Now when we talk about radiation, we are talking about one of two things. We're talking about the energy that's released or the particles that are released, and particles have mass. So now let's talk about the types of radiation, the particles and the energy. The first particle is a proton, and it is denoted by this symbol right here, the hydrogen atom symbol with an atomic mass of 1 and a mass number of 1. It's positively charged, and it's located in the nucleus. A proton we also call a hydrogen nucleus. Now most cosmic rays are protons. Cosmic rays are the energy that comes from outer space, and it comes on a fairly consistent basis and hits the atmosphere. And those cosmic rays that hit the atmosphere energize the atmosphere, and what happens, common things that happen are the aurora borealis. So if you look at this picture and look at this video from the space station, it doesn't actually show the cosmic rays hitting the Earth, but what it does show is when the cosmic rays do hit the Earth, they interact with our atmosphere in a way that gives off light. Another thing that cosmic rays do is they keep our carbon-14, which is a radioactive isotope of carbon, at a fairly consistent level in our atmosphere. We'll talk about that towards the end of this video. Carbon-14 is a radioactive isotope used in carbon dating. The next type of radiation is a neutron, and it is denoted by the symbol lowercase n with a mass number of 1 and an atomic number of 0, or n with a superscript of 0. It is a neutral particle in the nucleus of an atom. Next one is the electron. Now we've talked about the 3 subatomic particles, or we're about to talk about the 3 subatomic particles that you already know about, the protons, neutrons, and an electron. An electron is also known as a beta minus particle. The symbol is a lowercase e with a mass number of 0 and a charge of -1. Now if you notice, we put the atomic number as a -1. I'll explain that in just a minute. The mass number is 0 because it takes about 2,000 electrons to equal the mass of 1 proton or 1 neutron. So it's a very, very, very small number. It is also, the symbol is also denoted by the Greek symbol or letter B, beta, with a negative symbol, and a lowercase e with a negative symbol. These are negatively charged particles that are not located in the nucleus, and they orbit the nucleus randomly. Now a positron is also called a beta positive particle. It is an electron that is positively charged. We call these pieces of matter antimatter when an electron is positively charged, but it still has the mass of an electron as we know it, which is about 1 divided by 2,000 mass of 1 proton or 1 neutron. Now, there aren't very many of these in the world. The positrons, they don't last very long because what happens is it is extremely attracted to another electron because of their opposite charges, and when they collide, they totally annihilate one another and turn into energy. Now, because there's so few of them, they just don't exist for very long. a positron and an electron, their mass is so small that the amount of energy that they give off is so small we would never feel it if it's just one electron and one positron. Okay, next type of radiation is the alpha particle, and that's simply a helium nucleus. It is denoted by the chemical symbol He with a mass number of 4 and an atomic number of 2, and it is also denoted by the Greek symbol alpha. Now, it is the first radioactive particle discovered by Ernest Rutherford. And the last type is the gamma radiation. Gamma has no mass at all. It is truly an electromagnetic radiation. No mass and no charge. And it's denoted by the chemical symbol gamma, which looks kind of like a Y. All right, the alpha particle has a positive charge, and because it has a mass number of 4, it is the largest, or the most massive of the types of radiation that we have. And because it is the largest, it is the slowest. And it can be stopped by a piece of paper, so it is the least damaging of the radiation. Next one is the beta minus, or the electron. It has a charge of -1. Now it still has mass, so it cannot travel the speed of light, but its mass is so much smaller than an alpha particle. It can travel faster than an alpha particle, but it can be stopped by plastic or aluminum foil. Now our beta positive particle is, remember, just like a beta negative. The only difference is the charges are different. Beta negative is negative charge and beta positive is positive. It has the same mass as a beta negative or an electron, so it travels the same speed, which is faster than an alpha particle but less than the speed of light. And it can also be stopped by plastic or aluminum foil. Last one is gamma radiation. It has no charge and it has no mass, and because it has no mass, it travels at the speed of light. And it takes thick lead, very thick lead, or concrete to stop it. What happens there is the lead or the concrete will absorb that energy. And this is why they put lead aprons on you when you go to the dentist for x-rays. Now, x-rays are not as energetic as gamma radiation. It takes lead to stop the x-rays because they are a type of radiation as well, and they have no mass. All right, now let's talk about isotopes. This is a review. You should already know most of this. We're going to review it because isotopes are a huge factor in radioactive decay or nuclear decay. Isotopes are simply the same element, but they have a different number of neutrons. Now, there are two ways to identify isotopes. We call that the hyphen notation. It is simply the element name with a dash and the mass number. Now, remember, mass number is the number of protons plus the number of neutrons. So if we're talking about oxygen, that has an atomic number of 8 and a neutron number of 8, the name of it would be oxygen 16, because 8 plus 8 is 16, and that is one isotope of oxygen. The next one is the chemical configuration, and how we would write that is the chemical symbol of oxygen, which is O, capital O. The mass number goes on the upper left-hand corner, and remember, that's the number of protons plus the number of neutrons. On the lower left-hand corner would be the atomic number. You get that off the periodic table. And if you subtract these two numbers, you can tell how many neutrons this isotope has. It would be 16 minus 8, which is 8, so this isotope has 8 neutrons. The last one is in the upper right-hand corner. That is the ionic charge. That tells you how many electrons it has, or it gives you a way to find out the number of electrons. And looking at this charge of oxygen, it says that it has 2 more electrons. It's a negative charge, so it has 2 more electrons than it has protons. We know it has 8 protons, so it must have 10 electrons. The hydrogen isotopes have special names. Most other isotopes do not have their own special names, but hydrogen does. Protium is the most abundant hydrogen isotope, and it has simply 1 proton, no neutrons. Deuterium has 1 proton and 1 neutron, therefore its mass number is 2. And tritium has 1 proton and 2 neutrons, and it has a mass number of 3. Deuterium and tritium are radioactive, and protium is not. Now, how you can tell, one way you can tell if it's going to be radioactive or not is by the number of neutrons in the nucleus compared to the number of protons. It is thought that neutrons in the nucleus are there as a binding energy to help support the protons to stay together, because protons are positively charged. They don't want to be next to each other. And in a nucleus, they are very closely packed. The neutrons are there to help keep them together as like a binding energy. But if you notice that hydrogen only has one proton, it does not need a neutron to bind it with another proton, because if there was another proton there, it would now be helium. It wouldn't be hydrogen. And therefore, it doesn't need it, and because it doesn't need it, that would be the most stable form, is just a proton. Once you start adding mass to an atom, an unnecessary mass, which would be a neutron, then it becomes radioactive and it wants to get rid of it. And when it wants to get rid of it, the nucleus will decay. And when it decays, that means it's going to get rid of something, either a proton or a neutron, or an electron if it's outside of the nucleus. And in this case, deuterium has an extra neutron that it does not need, and tritium has 2 extra neutrons that it doesn't need. So they are very radioactive, which means they spontaneously decay. So why are some isotopes radioactive and others are not? The reason why is the proton-neutron ratio, what I just talked about. It determines whether an isotope is radioactive. Generally, not always, but generally, elements with an atomic number of less than or equal to 20 prefer a 1-to-1 ratio. There are exceptions to that. Hydrogen is an exception, but in general, for every one proton that an atom has, it would prefer to have 1 neutron with that. So if it has 2 protons, it would prefer to have 2 neutrons. Elements with an atomic number greater than 20 prefer a 1 to 1.5 ratio. So for every 1 proton, it prefers 1.5 neutrons. Now remember, you can't have a half a neutron, you can only have a whole number neutron. And that's not the case for every single atom, it's just in general. Transuranium elements are elements with an atomic number greater than uranium's atomic number, which is 92. They are all radioactive. In fact, any element with an atomic number greater than 83 are radioactive, and the atom with the atomic number of 83 is bismuth. So the element that comes right after that is polonium, and anything after and including polonium is radioactive. Okay, so now let's do a couple examples for isotopes. We need to write the hyphen notation in the chemical configuration for an iron atom that has 23 electrons and 32 neutrons. Now remember, for our hyphen notation, the first thing we are going to do is we write the chemical name, or not the, the element name, which is iron. And then we do a dash, and then we write the mass number. Now the mass number is the number of protons. The mass number is the number of protons plus the number of neutrons. All right? So the number of protons in an iron atom is 26. And we're given the number of neutrons, which is 32. So our mass number is 58. So over here, iron 58 is the hyphen notation for this isotope. Now for our chemical configuration, the first thing we're going to do is write the chemical symbol for iron, which is Fe. And then in the upper left-hand corner, we put our mass number, which we've already calculated is 58. Bottom left-hand corner, we put our atomic number, which we've already looked at and saw that it was 26. Now up here at the top, we put the charge. In order to find the charge, we have to find out how many electrons that it has. And it says it has 23 electrons. So the charge is simply the number of protons minus the number of electrons. Oops, sorry about that. Number of protons minus the number of electrons. So we've got 26 minus, and it says we have 23 electrons. And that is 3. And that's a positive number. So our iron will have a 3 plus. Now it says, write the hyphen notation and determine the number of protons, neutrons, and electrons for this chemical. Now P stands for phosphorus, So our hyphen notation, we always write the element name first, phosphorus, and then a dash, and then the mass number. Our mass number is right here, so it's 32. So the hyphen notation for this chemical is phosphorus 32. Now we need to find the number of protons, neutrons, and electrons. Okay, the number of protons is simply atomic number, and that's given to us right there. So the number of protons is 15. The number of neutrons is simply the mass number minus the atomic number. The mass number is 32. The atomic number is 15, so the number of neutrons is equal to 17. Then our number of electrons. The number of electrons, if you look up here, this phosphorus has no charge, which means the protons have to equal the number of electrons, so the number of electrons would be 15. Now, I would like for you to write the hyphen notation and chemical configuration for the 3 isotopes of hydrogen. You can assume that each isotope is neutral. I'd like for you to do this on your own and then come back. So pause the video and then come back and check your answers. So pause the video, please. All right, here are the 3 isotopes of hydrogen: protium, deuterium, and tritium, and their hyphen notation and chemical configuration. Now, carbon-14 and radioactive carbon dating. Remember what I talked about earlier with the cosmic rays changing our atmosphere, the air in our atmosphere to carbon-14? Well, it has a lot to do with our radioactive dating, how we do this. Since cosmic rays are relatively constant, they're constantly changing the amount of carbon-14 in our atmosphere. And this carbon-14 will combine with oxygen to make carbon dioxide, and so will carbon-12. And then plants will take in that carbon dioxide to make glucose or sugar. And then animals eat those plants, and then other animals will eat those animals. So as we live, we're constantly replenishing our carbon-14, or constantly intaking carbon-14. Now, when we die, we stop taking in carbon-14 because we're no longer eating, the plants are no longer making glucose or performing photosynthesis. So it stops intaking carbon-14, and carbon-14 is radioactive because there are 6 protons and 7 neutrons. There are more neutrons in there than needed, so it tries to get rid of them. So how we work on the carbon dating is we take a small piece of that fossil and we burn it, and we convert it to carbon dioxide. Now, a certain percentage of that carbon dioxide will be carbon-12, and another percentage will be carbon-14, and this depends on how old it is, because the longer the fossil has been around, the less carbon-14 it will have because it decays constantly. It's just constantly decaying. So we take that carbon-14 and we find out how much electrons are given off, because it is going to decay into a nitrogen and an electron, and then we have a detector that detects the amount of electrons that are given off. So for every electron that's given off, that means there was 1 carbon-14 there, and that's how we can tell or how long something has been dead for, so how long ago it died.